now we're getting to learning. So in both problem 1 and problem 2, I gave you the parameters of the hidden Markov model. I told you the phi's, the transition matrix, and the emission distribution parameters. I gave it to you. Now in this case, we flip it. So instead of getting the parameters, now I'm going to give you a massively long sequence, okay? And the sequence is now given, and I ask you, given that sequence, choose the HMM parameters, the transition probabilities and the emission probabilities in some way, okay? And in this case, we're going to do maximum likelihood, and particularly what we're going to do is we're going to maximize the likelihood of the parameters for that. And that's learning, and that's what we'll look at now. Can you guess what the name of the algorithm will be for learning, or at least one of the algorithms? I'll spoil it for you. It's called the forward-backward algorithm. If we've done that, then we've done learning as well. Have you seen the forward-backward algorithm before?
I suppose backpropagations.
Yeah, so I do think it's worth saying that this backward algorithm here and this backward algorithm here is different from backprop. Okay, it looks similar. I mean, it sounds similar, okay, but it's quite different from backprop actually. There are similarities, right? You move forward through a graph and you move backward through a graph, and in that sense it's similar, but the algorithms are actually quite different. So we come to this highlight of this little series on hidden Markov models, okay, which is learning the parameters. The goal, aim of the game. I don't give you the hidden Markov model, I don't give you the parameters, I don't tell you the transition probabilities, and I don't tell you the emission distribution parameters. What I give you is a training sequence, a long one, okay? And I ask you, please tell me what are these parameters. We're going to use maximum likelihood. Now this is really a little bit of a chicken and egg problem. Let's say I gave you the state sequence. In other words, I told you, here is your observed words, for instance, and the parts of speech tags for these words is the following, and I give you the part of speech tags, so I give you the states. Then it's actually pretty easy to figure out what the transition probabilities and the phi's should be. In other words, if I give you the z's, the hidden state sequence, and I give you the observations, it's actually quite easy to figure out the parameters. Okay? Okay, so very quickly, how would you do this? If I gave you the z's, and I ask you, what's the probability of, let's just do this, transitioning from a verb to a noun? I ask you, but I tell you that with your training data, there's a sequence of parts of speech tags as well. This is a verb, this is a noun, this is a noun, this is a determiner, this is a noun, this is a pronoun, and I give you that sequence with the x's. How would you figure out what is the transition from a verb to a noun? Maximum likelihood estimate.
Can you just count the number of times it happens in the by all the verb transitions?
That's exactly right. You just count up how many times do I go from verb to a noun, and I divide that by the count of verbs. And that is the maximum likelihood estimate. Amazing. Okay, cool. The emission distributions, you can do something very similar. So sticking with the part of speech example, if I want to know the emission probability that when I'm in the verb state of observing the word water, then you would just count up how many times did I see the word water coming from the verb state. Okay, so how many times will water labeled with verb out of all the possible verbs. Okay, and again, that's the maximum likelihood estimate. Unfortunately for you, I don't tell you verb, noun, verb. I don't give you that sequence. I only give you the words. Okay, so we can't do that. Okay, because we don't have that. Okay, so that's very sad. Cry me a river. Let's flip it around. Okay, let's say I don't give you the label, so I don't give you the hidden state sequence. I don't give you the z. I don't give you the parts of speech tags. But I do give you the parameters of the hidden Markov model. Okay, so I tell you, here's your thetas, here's your X training sequence. Okay, if I do that, if I tell you this is your hidden Markov model, and I tell you this is the observation sequence, what can you do then? Use Viterbi. That's exactly right. You can tell me this is the best path through this hidden Markov model. You can even tell me this is the overall probability of observing your training data given this hidden Markov model. Okay, so basically you can solve problems 1 or 2 if I give you the hidden Markov model. And the nice thing is, exactly what Aya said, if I use Viterbi, I can actually label this thing with the most probable labels, with the most probable parts of speech tags. Okay, so that's really nice. So we've got this. Oh, that would be really nice if we have the parameters theta. Okay, but we don't. Okay, let's recap quickly. If I gave you the hidden state sequence set, then you can tell me the parameters of your hidden Markov model. If I didn't do that, but I did give you the parameters of your hidden Markov model, this and this, I gave you that, and I gave you your training data, then you could find the labels for that training data. You could basically label your data with that hidden Markov model. But we're screwed, right? Because I didn't give you what you need for either one of these. So we've got a chicken and egg problem. So what we're going to do, this is the idea behind the expectation maximization algorithm, okay? Or the forward-backward algorithm. Expectation maximization, what we're going to do is we're going to guess some random parameters. They're probably going to be bad, okay? But in essence, what we're going to do is we're going to guess a theta. We're going to label our data with that theta. So we're going to run Viterbi, or maybe do something slightly more better than Viterbi, right? Maybe we use the forward and the backward algorithm to get soft probabilities, okay? So we use that theta to label our data, okay? That's expectation. Under the model, what do I expect to happen, okay? And then what we're going to do is, given this slightly crappy theta, okay, we've labeled our data, and now using these labels, we're going to estimate our model parameters, okay? And they're going to be pretty bad to start off with, okay? Now we've got a new theta. We've got a new A and a new phi, which is theta, okay? We use that new A and new phi to label our data again, okay? Then we use the new labels. We update these guys, okay? Then we label the data again, tung, 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 tung. So it goes like this, okay? Does that make sense? Okay, cool. So that is exactly what the expectation maximization algorithm does. And we're going to look at 2 flavors of expectation maximization. The one is to do what I suggested, which is just use Viterbi, and that's Cassandra's approach about not worrying too much about these soft probability stuff. She's not a Bayesian, right? She just cares about the most likely path, and it will turn out to work pretty well, okay? So that will be the one version, okay? And that's called hard EM, hard expectation maximization. And then we will also do the soft EM algorithm. The soft EM algorithm actually takes the soft probabilities into account, okay? The fact that I can maybe be in one state and not, I can be in one state with a probability of 0.6 and in another state with a probability of 0.3 at the same point in time, okay? So that's going to be soft expectation maximization.